All right, guys. This proof here, okay, it's going to have very similar aspects to the proof that we did on Friday. All right, different shapes. Friday's was angles. This one's segments. There is a little bit of a twist in it that makes it ultimately different. But there are going to be, as we go through this, obviously, you know, the reason we'll do a proof is because it's a different statement than something else. Yeah, another statement that we may already proven or haven't proven yet. Okay, so whenever we do a proof, it's probably a new question. However, there are similarities that exist between proofs. Okay, there are chunks of statements that come in like groups or clusters of like 3 or 4. That when we instantly see the first one in a proof, we know then that the next 2 or 3 statements should follow directly from that. Okay? If we can recognize patterns and relationships inside our proofs, it will make our lives a little bit easier. If we can recognize that there are similarities between this proof and one we've already done, it's going to make our lives a lot easier. Okay? So I'll kind of jump back and forth between this one and the one that you guys did on Friday. What we want to do, let's just kind of analyze this kind of the way we did on Friday with the angles. Let's look at specific examples. Give me a number. 13. Okay. So what we're saying here with our given is that that segment there and that segment there are both the same, right? So let's say they're both 13. So that's 13. That one's 13. Give me a number less than 13. I'm going to use 2. Okay. Would you guys agree that that green stuff right there is an overlap? Okay. Whether it's 2 or 11 or 12, whatever it is, doesn't matter. But that's the overlap. Let's say that overlap is 2. Okay? If that overlap is 2, and I wipe away that overlap out of both those. So wipe away that overlap. Started with 13, wiped away an overlap of 2. What are you now left with? What number would you be left with? 11, right? And you see the segments A, B, and C, D, which would be representing that 11? That kind of makes sense? Okay. Is 11 equal to 11? Is that ultimately saying then that A, B is equal to CD? Okay. The idea about proofs, though, is that that's just one specific case. We want ultimately what we call the general case, which encompasses the infinite number of specific cases that could occur. So we would, in regards to proving this with specific values, we will say, okay, let's start off with 13.1 now, and do the same thing. And 13.2 and do the same thing. And 13.11, 13.112, and the infinite number of values that we could start off with. Does that make sense? And then we want to remove the infinite number of values that we could have removed. Well, that's impossible. We're not going to be able to do that. Okay? But using specific values might give us an idea or an approach that we can use. Hopefully you realize here that, you know, what we did is we removed something from both sides, right? Stated some things that were equal. We removed some stuff from both sides. This process is going to incorporate that, and it's going to be all-encompassing of every single situation as long as we start with AC equaling BD. Regardless of the numbers that are hiding behind those symbols, this should work. And this will be the reason why that is always true. So as long as you have an AC is equal to BD, I have fun over there. This is a blast. All right, so AC equals BD. All right. If you remember back to the question we did on Friday, okay, there were 2 angles that we were trying to look at and analyze And let me pop them up here real quick. We're looking at AEC and BED, right? Okay. So we're looking at that angle along with that angle, correct? Is there overlap? What angles overlapping? Okay, BEC or angle 2, right? That's what the overlap is. Notice that we made mention of that, right? We need to do that here as well, okay? Whenever we see overlap, it's going to be important to talk about that, okay? So in regards to the two segments that we had, what's the overlap? BC. Let's make note of that. BC equals BC. And all we're doing is telling the person that's reading our work is that that number that's hiding behind that symbol is the same number every time we see that symbol. Okay? So BC equals BC says whatever that number is equal to itself. What's that property? What's that reason? Reflexive. Now, BC is kind of a weird phrase here. It's a weird thing. It happens occasionally. Sometimes we see it multiple times in a proof. Sometimes it doesn't exist at all in a proof. But what we're going to find out is that BC equals BC is actually a statement that can kind of float around in our proof. Could be statement 2, but maybe it doesn't have to be statement 2. Maybe it could be statement 3 or 4. Okay? Because what happens is that statement is independent. Okay? Nothing is really going to impact that statement. All right? And we'll talk about that as we conclude this proof. But if we're going off that handout I gave you on Friday, I gave you the 7 kind of steps to navigate a proof. I think most people would probably end up with this as statement number 2. Okay. The next thing that we're looking at. Okay, so we wrote our given down. We looked for vocabulary words. We then looked at our picture and see if there's anything overlapping. The next thing is to say, okay, if we're looking at our picture and it's got segments. Segment addition is probably going to drive this question. Okay? So it'll be the process that kind of governs the entire procedure. So let's write some segment addition things down. Okay? And if we look at this, there's probably 3 segment addition comments that you can make. All right? I'm going to write down one for the blue one. What would you guys write for that blue segment? What would you write in regards to segment addition about that? No, you know, AB plus BC equals what? Equals AC. Okay? So AB plus BC equals AC. Okay, segment addition function. If we did that for the blue, we should be able to do something similar to the purple, right? So let's write something down for the purple. Let's write BC plus CD equals BD. It's going to be the same reason. Okay, so I'm not going to create anything new. I'm going to another statement or a reason over here. Still segment addition. Let's jump back up real quick to the one we did on Friday. Is this an angle addition idea right here? Where my cursor is? 1 plus 2 equals AEC. 2 plus 3 equals DEB. Pretty similar to what we're seeing here. Okay. Now, okay. Now what we want to do, we've effectively looked at our picture and our given, and we've written down every single fact that we know to be true. And I said there's a 3rd segment addition that we can write. Okay, let me write it right here. You guys don't have to write this down. Would you guys agree that that's true? AB plus BC plus CD equals AD? Absolutely true. Okay? And there's nothing wrong with writing things in my proof that are true. But their use or their their contribution to the problem and the overall proof may not be useful. Yeah, or may not, there might not be a contribution. If I write AB plus BC plus CD equals AD, it's absolutely right. Okay, and you can put that in your proof. But as we go through the other steps of this proof, you're going to see that we never target that. We never even address that again. It's not going to be a necessary fact. Okay, so we leave it out. That's kind of the idea that I mentioned. I think it was Thursday. When we do proofs, they're like rough drafts. So if you're a person that writes a proof and it's got 12 steps in it, and you got all these true facts, but Mr. Fay does it in 4 steps in class, hopefully then you go back and say, okay, what 8 steps did I have in here that really weren't necessary? Does that make sense? And you always got to go reflect, okay, how can I condense my proof by removing things that I didn't use, things that weren't really a necessity for the proof. Step 4, or statement 4. I'm going to write the exact same thing I have in statement 1. I'm going to write an equation that is exactly the same as number 1. But it's going to look different. Okay? It's going to provide an equation, so it's numbers, right? So with the left-hand numbers, the numbers on the left-hand side, to be exactly the same as the numbers on the right-hand side, and they're going to be exactly the same statement as number 1. Good. Okay? So he's seeing that if I'm going to rewrite statement number 1, I need an AC here, right? I said I'm going to write it so it's different looking. Well, AC, we said was the same thing as AB plus BC, right? So AB plus BC is that kind of alternative version, okay? Looks different, but it's still the same number on the left-hand side of my equation, right? Okay. Can I do the same thing with BD? Oh. Yeah. It's BD, okay, that's the statement right there for that. Distance, has it been defined as BC plus CD? So BC plus CD. You hear me say the word defined. That's basically what we're doing. We're redefining, relabeling, rewriting, redescribing, maybe another way of thinking about it, the components that made that equation. Okay? But it still has to be the same equation. It has to say the same facts, and this does. So what is it by taking that AC out and then putting in its place something that we knew it was equal to? Substitution. Okay. And now here comes the benefit of knowing what we wrote in statement 2. In statement 2, we said BC equals BC. There's a number BC, and it's equal to some other number BC. And those numbers, if they're equal, they got to be the same thing, right? Does that tell me then, when I look at this 4th statement here, that there's a number right there, and there's a number right there, and if those 2 numbers are the same? Does that make sense, everybody? Okay. Well, if they're the same, so think about this. If you had an equation, like if you had like 2x plus 3 equals x plus 3, what could you do with the 3's? Yeah, just subtract them out. They wipe each other out, right? Okay. So if that and that are the same, let's wipe them out. What would you be left with? You wipe them out? AB equals CD. Is that what we wanted to prove? Yeah, okay. And that's kind of the thing that we talked about Friday. As we went through this, I never, in the whole procedure, told you to look at what we're trying to prove, right? Okay? We just went through some steps and facts and linked some things together, and that prove statement just kind of fell in our lap. Okay? That's going to happen quite a bit. There will be times where we do want to look at that, but right now, guys, I'm not even really concerned about when you see one of these proofs, don't even concern yourself with trying to get there. Okay? Just write all your facts down and start linking things together, and eventually that will kind of fall out of the problem for us. Okay? So what was it when we wiped that BC away from both sides? Would you guys tell me that property was that reason I can keep? Yep, subtraction. advice for you when you get to the end of course exam. Through a lot of stuff that we do, guys, abbreviation is fine, okay? Just to expedite some of our processes, get through them a little bit quicker in class, see more examples. And even sometimes there's going to be, for like sentences that we have to write, there might be some abbreviations that we use to eliminate some of just the writing aspect of the course. When you get to the end of course exam, you're going to want to try to control the way you abbreviate and control the way you condense your statements. Because if I abbreviate SUBT on my end of course exam, there's a potential that your exam is going to be graded, if it's something like a type, be graded by an algorithm, okay, which is just basically a computer program that we feed information into, and it starts to learn how to read. Does that make sense? Okay. You guys use turnitin.com. When you turn paper in, does it tell you your feedback of how much has been plagiarized, that kind of stuff? Well, basically, let's look at the structure of your sentences and your work and all that kind of stuff, and comparing it then to all the endless documents that's been fed into, and it's just doing a comparison, okay? Well, if we start using, like, we think about all the things that have been fed into maybe this algorithm that's grading our work on the end of course exam, and none of them use SUBST as substitution, none of them use SUBT as subtraction, it's going to see those words and not know what to link to. Does that make sense? So you want to use minimal abbreviation when we're working on those tests. Just little things that I wish we didn't have to talk about, but we do. Now, what is the benefit of a proof like this? Okay? Let's give you a picture here. We'll see this later on in chapter 4 or 5, I believe. Okay. Later on in chapter 4 or 5, we might be provided with that picture and be provided with the exact same given statement. Okay. We'll probably try to prove something completely different, but we want to eventually show that that segment right there and that segment right there are maybe equal to one another. Does that make sense? Okay. Well, if I'm doing this inside that proof, let's say that proof all by itself is maybe 5 statements, okay? But this needs to be used then after those 5 statements. So that would be 10 total statements that we have to write out. Is that right? Okay? We don't want to write out 10 statements. We want to write out 5 or 6. Okay? So what we do is this idea, I'm providing a picture like this anywhere, provide that information, that if-then information, okay? And I get the conclusion that A, B, and C are equal. We can condense this as what we call the common segment theorem. There's actually 2 versions of this theorem that we're talking about. There's an additive version that we just did, a subtractive version. But we're getting what we call a common segment theorem. And if this idea needs to be used in another proof, instead of writing all 5 of those steps, we can just make the conclusion right away. AB equals CD, and it's because of this common segment theorem. Okay? Basically what a theorem does is it takes a grouping of true statements and facts that get me from a given piece of information to a proved situation, proved statement, that we can use inside other proofs to condense other proofs. Is that right? If there's just no time, that's always going to be true. And no matter what I start with, if AC and BD are equal, and there's that overlap of DC, I'm always going to have AB equals CD. Always, 100% of the time. So the next time I see that, do I want to write out those 5 steps? No. I'm going to write out 1 step, and it condenses all that into 1 step. Is that all right? So that's the idea. We haven't talked about theorems, haven't defined them yet, but we'll get there. That's the purpose of it. Okay, basically to condense our work, to make our lines of thought a little bit more concise, losing my voice, puberty. All right, let's do this one. This is the first one I think on that handout. So this one's more aligned with, if we look back to the other one, look back to the one we did on Friday, those used algebra. We had to create the algebra. We had to introduce it, which we still kind of have to do here. But you see that there's expressions here that we're going to also use. Traditionally speaking, when we do proofs, we're only going to see the x, the 3x plus 20, this kind of stuff, for like the first 2 or 3 days. And then it slowly vanishes. These types of proofs are just to get us kind of in the flow of how to work with proofs. It's taking kind of a step back from something we've already done. We've already done that. If I just gave you the problem up here, if I just gave you this and said solve for x, you guys have done that. We did that in chapter 1. Yeah. But now it's said, okay, we already know how to do something. Let's step back and talk about why we were able to do that, why those steps will be able to be conducted on. So this first one, you'll see this every once in a while, where the given is just a picture. And you say angle CD, that's what you're given. So write that down as a first statement. It says prove x equals 40. Again, whether I want to address that right away or not, I don't care. I'm just start working and see hopefully that 40 just kind of falls out of the problem. Okay? So CDF is provided, that's my picture. There's no vocabulary there, so I don't do anything with that. And we'll go look at my picture next. And this is the thing that we talked about a couple weeks ago. When you look at your picture, you can tell whether 2 angles are a linear pair or not, can't you? And they form that straight line, CDF, CF. You can say it's a linear pair. So that's what they say here. Okay? And I would probably be a little bit more specific on how they write, because I would probably input another statement in there that says CDE and EDF are a linear pair, a definition of a linear pair, and then I would make this statement. Okay, so they kind of glance over something, which is fine. We'll talk about that as we move on this question as well. But they say that these are supplementary. And the reason they're supplementary is because we had a postulate in chapter, in section 1.8 said, no, 1.6 maybe, said if 2 angles form a linear pair, then they are supplementary. And they wrote out what that postulate said. We had a name for it. It's called the linear pair postulate. Okay? If you don't have to use it, you can either write it out the way it's set up there, or you can write linear pair postulate. Okay? But what happened here? We just introduced a what? What kind of phrase, what kind of thing is that? Supplementary. It's a vocab word, right? Vocab words lead you to new facts. Okay? So what we're going to look at is, okay, what does the vocabulary word supplementary mean to us? If we look in the glossary, it's 2 angles whose sum is 180, right? Is that what we're writing here then? 2 angles whose sum is 180, right? Okay? So we take the vocabulary word, this is what that handout I gave you did, take that vocabulary word and write down what it means for you with your specific situation. So with our point C, D, F, and E. Okay? So this would be definition of supplementary angles. Okay? They introduce a vocabulary word. We figure out what that vocabulary word means for us. We write that down, and the reasons go to the definition of that vocabulary word. Okay? If you're a person that wants to kind of do what they did in that first step with the linear pair or supplementary statement, if you so right here, instead of writing what we wrote 5 words there. Okay? If your person says supplementary angles are 2 angles whose sum to 180 as your reason, that's fine, because that is what the actual definition statement says, right? Okay? I think just most people are going to prefer to condense that. Okay? All right, so now what do? What do they do from step? Yeah, they saw CDE, with the same thing as X. They saw EDF, that's the same thing as 3x plus 20. So they replace those. Okay? So now the next thing, and I'm going to leave this up to you guys, how you feel comfortable stating this or representing this when it's on, when you try to type it out, write it down, whatever. You've got multiple options. If it's in a drop-down window, maybe your multiple options kind of get narrowed down to the only ones that they choose, or maybe I think we got maybe 3 ways that we can write this or explain this. Your drop-down window might only have one of those, so we'll show you all of them. We talked about the fact that if they had, basically looking at that x plus 3x turned into that, right? Okay. Last week we did this procedure, right? Factored the x out, and became x times 4 or 4x. You remember what we called that? What math excel is? Yeah, math excel is saying that's distributive property. Okay, so that might be the only option in your drop-down window that they give you. Okay, I'm a fan of this just because I understand inside that is this information. Right? That's what most people are familiar with and comfortable with. Yeah, so if you want to write that down by hand, that's fine. Someone earlier said this, which is a great point. We took that, x plus 3x, did we replace it with what it was equal to? That make sense? Combining like terms, essentially substitution. You want to view it that way? So that's fine. I think those are the kind of the 3 main techniques, or main reasons why you might argue x plus 3x changes to 4x. Inside that stuff, though, there's probably a few steps algebraic that we should probably maybe talk about if we wanted to. Okay? Because really, when we were doing this last year, you don't have to write this down. But maybe inside that step there to that step, you would do this. We did that last year. All I did is shift my parentheses, right? Because the associate property of addition allows us to do that. So that'd be my reason. Okay? Now, there are times where it's do, maybe it's not. I would say that most of the time with our algebra like that, we're not going to use the associate property, commuter property very much because we're making the assumption that who's reading our work? Our peers are people that are above us, right? In regards to our intelligence. So we're going to say that either our peers or the people that are reading this work understand that when we go x plus 3x to make it 4x, we don't need to tell them how to use the associative property, commuter property, that kind of stuff, right? So we kind of glance over that kind of additional set of procedures that are occurring between those. All right. So what do they do then next? They're going to put 4x plus 20 equals 180, and 4x equals 160. Subtraction. And then what do they do? Division. All right, so most of the time, I think you're seeing that when we have to fill in our reason, that reason is the answer to the question, what did we do next? Or what did they do? Or something like that. Okay? So if you can talk yourself through what did you do, what that reason was. Okay? Do you guys think this is fairly straightforward so far? Okay. My fear is that we might get a little kind of withdrawn from this because it's right now maybe simple. It'll be just like that, like snap of fingers with this stuff is just mind-blowing. Okay? So please understand why I'm going slow and why I'm kind of targeting and talking about these individual steps as much as I can. Okay? Because at some point, and it'll always be like it seems like it's overnight, this stuff starts to get a little bit more complex. All right? But if we understand things that Mr. Frey talked about through these easier questions, then we can understand that idea, that concept when things do change a little bit. We'll do one more with you. There's one on there that's like KM or KL. That one. If you just real quick kind of compare this one to these are the last two, right? See how these two, they don't have any algebraic expressions in the picture or anything like that. There's no stuff, there's no algebra that we have to do in regards to like X and that stuff. There will be algebra that we do here, but we have to generate that algebra, okay? So we're going to see a couple of these in our homework tonight. They're kind of like this, but they're going to be short-lived. They're not going to be around very long, okay? We'll start doing more proofs, kind of like these. Okay? Before we get to that one, we think about this one. Like I said earlier, we did the problem before, right? And we did. Now we can sit back and think about, okay, what was allowing all those times that we did that problem? What was allowing the math to work? Okay, this set of steps here, these 5 or 6 steps, are what's allowing that math to take place and allowing it to work. All right, this one. Write our given down, right? That should take us into vocabulary. Is there any vocabulary? Nope. Okay. So I see too many with any vocabulary yet. That will change. Okay, so the next thing is to look at a picture. This picture is a little bit more simplistic than what we've seen so far. There is no overlap, right? Okay, if I'm going to have segments overlapping, I got to have at least 4 points. If I'm going to have angles overlapping, I got to have at least 4 rays. So we don't have any overlap here, so I don't need to use the reflection property at all. But we are dealing with segments, right? So I'm dealing with segments, what probably drives the problem? Segment addition. So write a segment addition statement. KL